Good morning. So today what I'd like to do is to cover two sections of chapter 9. These are the final sections of the chapter that we'll cover. The first one is called hybridization, and that's section 9.5. So I'm going to cover hybridization. And then 9.6 is entitled molecular orbitals. And these are two theories of chemical bonding in primarily organic compounds, but inorganic compounds as well. These are both, particularly hybridization is a widely used theory. Both are widely used in advanced chemical theories, bonding theory for covalent compounds. Okay, so we're still talking about covalent compounds. So we're going to talk about hybridization first, and then we'll move on into molecular orbitals. Okay, so for hybridization, so let's begin with that. Let's remind ourselves of this idea of atomic orbitals. Right, we'll call them AOs. Now, we actually often might refer to them more technically as hydrogen-like atomic orbitals. And we'll just leave the hydrogen-like off of the title and just call them atomic orbitals. But really what we're talking about are those orbitals that were calculated and then measured for the hydrogen atom way back at, halfway through chapter 6. Okay, it wasn't that long ago, but we've covered a lot of topics since then. So if you recall, we said, hey, you apply the wave mechanics equation to the relatively simple, seemingly simple two-body system. You have a proton at the center and one electron around it, and you get these wave functions, you get these orbitals, we call them, right? And so we said, hey, there's these orbitals, the simplest one, the one at the lowest energy. There's the nucleus at the center. We called that a 1s orbital, right? It was spherically symmetric. The electron is orbiting, is occupying that space around the nucleus. And then we said there was another orbital that was higher in energy and is bigger. And that was the 2s, higher in energy and larger, right? So now the electron, any electron that's in that orbital is occupying a larger region of space than it would for the 1s. And then we said, hey, but there's also these other orbitals, right, that have different shapes. These ones are the ones that had the different angular momentum quantum numbers, different values of L, right? And so we said, hey, there's the two, that looks like a heart, right? Let's go to erase the whole thing. There we go. So we called those lobes, right? They're supposed to be symmetric, so those lobes are supposed to be the same size. I almost got it right. Okay. And then we said there's even, higher energy ones like the 3D and 4F, if you want to go that far. But, we recognize that, right, you can have like larger ones like the 3S. And maybe the 3P. And I'm going to ignore like the details of these orbitals, Remember, these are what we call probability distributions. Okay. And there's something called a nodal plane through some of these orbitals. We're not going to worry about that for right now. There's also something called phase, for the orbitals that have lobes. There's different phases. We don't need to worry about those kind of wave details right here. If you become a chemist, you'll learn about them in more advanced courses. But those are called atomic orbitals. And what we want to do right now is we want to talk about how a central atom can maximize the strength of its bonds to other atoms. So essentially the idea here in hybridization is that you imagine a central atom. So typically it's actually a carbon atom. Hybridization is very useful for the carbon atom. Carbon can do some kind of amazing things. It can bond to maybe just one other atom. So carbon monoxide, for example, is just one carbon, one oxygen. Or it can bond to two different atoms. So for example, CH2 or CO2, right? Carbon dioxide, two surrounding oxygens. It can also form bonds to three different atoms, like formaldehyde, right? So actually, let me show you these. So you could have, carbon monoxide. So the carbon's only bonded to one atom. You can have carbon dioxide. The carbon is bonded to two atoms. You can have formaldehyde, CH2O. Oops, sorry. CH2O. There, the carbon is bonded to three different atoms. And then you can have CH4, where carbon is bonded to four different atoms. So that's, there aren't very many elements. Actually, I don't think there's really any elements that have sort of the variety of potential chemical bonds. So one of the things we want to do is we want to be able to describe the ability of an element like carbon to form this variety of different types of compounds. If you take sodium and chlorine, they form one type of compound, sodium chloride. But if you take carbon and oxygen, you can make carbon monoxide, you can make carbon dioxide, you can make formaldehyde, you can make all sorts of different things. So how do we describe that? And the idea is essentially this. It's what we call valence bond theory. And hybridization is a subset of valence bond theory. And essentially it's the idea is this, is that orbitals overlap with one another. To form covalent bonds. Okay, so covalent bond is a result of the overlap of atomic orbitals from different atoms. So for example, if we have a carbon with a 2p orbital and another carbon with a 2p orbital, if those orbitals overlap with one another, then we have a covalent bond. So the overlap is equal to the covalent bond. So the greater that overlap, the argument goes, the more region of space that they're overlapping, the stronger that bond will be. And the smaller the amount of overlap, the weaker the bond will be. Okay. Now, in general, atoms, will form bonds with other atoms and will do so in such a way as to maximize the strength of the bonds between them. So in general, an atom doesn't really try to make weak bonds. It tries to make the strongest bonds it can. And that's really just, it's a phenomenon of energy, of lowering the energy of the molecule. The stronger the bond, the lower the energy of the molecule, and the more stable that molecule becomes. Okay, it's about energy minimization. So imagine that you have these two carbon atoms with these orbitals, and those orbitals are, overlapping like this, right? So I'm only showing part of the orbitals there, right? This would be our region of overlap. That's what we're going to call the overlap region right there, okay? And that's our covalent bond, that overlap. And we're going to leave aside for now what happens when those orbitals overlap. When we get to molecular orbitals, we'll say that in fact those orbitals actually interact with each other, and they add to each other according to wave mechanics and form new orbitals. But for valence bond theory, of which hybridization is a part, right? So hybridization is a part of valence bond theory. We're not worried about that. We're just saying, look, these atoms are going to have these orbitals. They're going to overlap. The greater the overlap, the stronger the bond. So stronger bonds have greater overlap. So let me show you a couple of different ways in which they can overlap. I showed you one right there. Here's another way they can overlap. And it may seem a little bit odd. So let me redraw these ones. There we go. Okay. Remember, there's also the other side of the orbital, right? Goes like that. So I'll draw the full orbital in there, right? Okay. And then there's our overlap. So that there's our bond. Now, if you can draw a line through the orbitals and through the nuclei of the atoms. So see how I'm drawing an imaginary line like the equator? It's going through the orbitals, right? In the bond, the orbitals in the bond. But it's also going through the nuclei of the atoms. We call that a sigma bond. Any bond in which you can draw a line through the orbitals that make the bond and through the nuclei of the atoms that are in that bond. That is called a sigma bond. And the symbol for that is the Greek letter sigma. Remember, sigma is a Greek letter, and the uppercase is used in mathematics, right? That's what we use for summing things, for adding things up. So that's sigma. And then the lowercase sigma is this one right here. It's like an S. Sigma is like S, really. And for the sigma bond, we use the lowercase. Now, why do we use that? It's analogous to S because this is the Greek letter S. We're really saying that S orbitals form sigma bonds, and even though I'm using p orbitals right here, in fact, it's actually perhaps the most common sigma bond is the bond that you get between S orbitals. At least one of the atoms has an S orbital. Okay. Now, there's another type of bond where the orbitals are parallel to each other, but they're not pointing toward each other. And this is interesting. So I'm just drawing another p orbital, just like I drew before, but now this p orbital is now up and down, right? It's vertical, right? So what I'm going to claim is that, in fact, even though it doesn't look like it, there's actually orbital overlap here too, in two different regions of space, actually above the carbon atoms and then below, according, from our perspective, right? And this one we're going to call a pi bond. Pi, right? So again, we're talking about the Greek letter pi. I guess, uppercase pi, lowercase pi. I guess we typically use lowercase for this, and that's a p, right? And as you imagine, okay, p, right? So we're really talking about p orbitals. Okay, so typically pi bonds are observed when you have the overlap of p orbitals from two different atoms. So that's called a pi bond, and that's the second type of bond. And it's really, what's the difference between a sigma and a pi? It's geometry. It's like the how the orbitals are oriented geometrically. If you can draw a line through the orbitals that make the bond and the nuclei, that's called a sigma. If you can't, we're going to call it a pi bond. Okay, there could be a better technical definition of the pi bond, but we'll use that for now. So you see right here, so I'm claiming the overlap is here and here. There's two regions of overlap, but you see the overlap is not very great, right? In fact, they look separately, but that's just a manifestation of how crudely I'm drawing this. I'm using the symbol C for carbon, but there's no little C's in nature. There's like little points, which are the nuclei, and then the core electrons are out there. So more accurately, those nuclei would be closer together. The orbitals would spread out a little bit more, and then you would see a little bit of overlap. I'll show that to you in just a second. Okay, so notice how you cannot draw a line through the nuclei and the region of overlap, right? See, this is the region of overlap up here. You'd have to draw a separate line to get through the nuclei. So then, we're going to call that a pi. We're going to call that a pi bond. And let me just real quickly show you a little bit better depiction of this. I'm going to make the orbital, all I need to do is just make these a little bit closer to each other. Okay. Now, see how I'm drawing the orbitals here? Still not doing a real good job of it, you guys, but let me show you here. There we go. See how I'm drawing that? Now we have two regions of overlap. Okay, that's a little bit better. Now, why did I draw those p orbitals in the pi bond? Remember, this is the pi bond and this is the pi bond, and then the one in the center is the sigma. But we're not going to claim this is two pi bonds. It's just two regions of overlap for the same orbitals. If it's the same orbitals, it's not a different bond. So there's just one bond in those two regions. Remember, when we draw these orbitals, these are typically what we call 90% probability. But it's not 100%, because remember, the orbitals are actually exponential curves, essentially. So they decay away. But so what happens with an exponential decay, so this is distance from the nucleus, is that, you know, it's kind of arbitrary how far you want to go out. If, like I say, here's 90% of the probability, you know, so here, that's 90% of the probability. There's still 10% probability here, which essentially means that even though I drew them this way, this is crude over here. This is actually not very accurate, but we do it that way just to kind of, so you can see it a little bit better. This is more accurate. This might be 95% probability or 96% probability. And so there will actually be some overlap here, but that overlap is actually weaker than it is here. These two orbitals are pointing directly at each other. They're the same size and the same energy. When things are the same size and same energy, they tend to interact with each other more strongly. So that's going to be a nice strong bond. So generally sigma bonds are relatively strong. The pi bond, however, the overlap is weaker, and so it's not as strong of a bond. So pi bonds are generally weaker than sigma bonds, okay? And you can look at some of the energies of this. It's kind of interesting. Like if you look at two atoms that can form either a single or double bond to each other, often what you find is if they form a single bond, that bond might be 300 kilojoules per mole. But if they form a double bond, it might be the total 500 kilojoules per mole. So that means the first one's probably 300 and the second one is only 200 kilojoules per mole. So the second bond is weaker than the first. So in general, when atoms form bonds to each other, if they can form more than one bond, the first one will be a sigma because that's the strongest. Again, these atoms are trying to lower their energy by forming bonds. That's why molecules form, is an atom has these electrons. If those electrons can interact with other atoms, that lowers their energy overall. So the first bond tends to be nice and strong, a sigma bond, and then the second bond is going to be a pi bond, which is going to be weaker. And if you have a third one, that'll be a pi bond as well, and that third bond will be weaker than the first one. Okay. So that's essentially just a real brief introduction to valence bond theory, the idea of overlap, and then also hybridization, kind of giving you an idea of the two different types of bonds, which we'll call sigma and pi. Okay. Now, I want to go over one of the types of problems in ALEKS. Okay, but before I do that, let me give you a little bit more background, okay? So let's talk about types of hybridization. So you can use synonymously with the word hybridization, you can use the word mixing, because that's really what hybridization is. Hybridization is the mixing of atomic orbitals. So what you can do is you can say, hey, if I have an s orbital and I mix it with a p orbital, so I'm just going to pick a p orbital that's sort of like this. Okay, this is called a p, right? What you get when you mix those are two new orbitals. So I put an equal sign, right? When you mix those two together, remember they're waves, so waves can add to each other, right? If you have a voice coming through the room and another voice coming through the room. Sometimes those waves can mix together and form interesting sounds. So what you get is, you're putting in two orbitals. You get two new orbitals. And here's the nucleus, okay? So this is within the same atom, right? So this is an s orbital from one atom. This is a p orbital from the same atom. Remember, like carbon has 2s, 2p. Phosphorus has 3s, 3p, 3d, right? So you can mix these orbitals together. And what you get is you get two new orbitals. One looks like this. I'm going to ignore, there's actually like a little tiny region over here. So you get a little nub over there. Okay, actually, you know what? I'm sorry. Let me draw it this way. But most chemists will ignore that little nub down at the bottom. I'll leave it there for now, but in the future, we don't need to worry about it. And then this is called an SP. Now, the terminology SP refers to, that's the name of the hybridized orbital, the mixed orbital. The name is given by how many s orbitals are mixing with how many p's. So if you mix one s with one p, we call it sp. Right? Now you get a second orbital, and that one looks the same. It's just converted over on the other direction. So there's your little nub there. Again, we normally only draw this part right here. We just ignore this one down here. Okay. So in fact, I'll erase it. Just because one, that little nub is usually not involved in bonding, and then two, it makes it harder to draw, right? It's just kind of in the way. Okay, so a couple things I want to say. One is, if you put in two orbitals and you mix them, you're going to get two orbitals out. And they're called sp. And the naming is how many s's, how many p's. You just put that together. Okay. Now you can't really mix two s's. The most you can do is one. You're going to mix an s with a certain number of p's, 1p, 2p's, or 3p's. Okay. So these are called sp hybridized orbitals. And one of the things that we notice about them is they're kind of directional. They're certainly more directional than an s orbital, right? There is no preferential direction for an s orbital. It's spherically symmetric. But a p orbital has some direction, right? A p up and down, right? But look what happens. You get these two orbitals when you mix them together. One is pointing in one direction, the other one's pointing in the other direction. And so you've taken orbitals that are kind of, the s and the p that have different orientations, and you've turned them into very specific directions. Each of those sp orbitals is pointing in one specific direction. Okay. And that makes them very good for bonding, because if an orbital is pointing directly toward another atom, you're going to get a good amount of overlap. And so hybrid orbitals appear to be the way, a mechanism for the atom to take its atomic orbitals that are not that directional and mix them together to make directional orbitals that can make stronger bonds. That's essentially the idea. You can replay that again, but that's essentially what's going on. Okay. So now you can also have a second scheme. I'm going to give you 3. And the second scheme is where you take an s orbital and you mix it with 2 of the p's. Because remember, there's 3 p orbitals, right? So plus. Ooh, I didn't draw that very well. Let's make I just need to make a little more room here. That's all. Okay, remember we had like px, py, and pz. So let's say this is x and y, just arbitrary. So now what are you doing? You're mixing an s, but you're mixing with 2 of the p's. So you get 3. So right, if the number of orbitals you put in is going to equal to the number of orbitals you get out. There's a conservation law with that. And now what you get is kind of interesting. You get 3 orbitals. So there's one. And this one comes down here. And then you get a third one, which is like that. And we're going to call them sp2. Remember, that little dot there is the nucleus of the atom. Okay, so I just want you to remind yourself of that. That's the nucleus. Okay, so the shapes of the orbit. See, this becomes very visual, right? And that's a powerful aspect of this, is it's a very visual technique. So that's why organic chemists like it. They could, you know, when you start to see things, you see these orbitals and they mix, and it gives you some ways to use part of your brain for the visualization of a chemical reaction. So when organic chemists are looking at a chemical reaction, they're visualizing these orbitals overlapping with each other and breaking of orbitals and stuff like that. Breaking bonds anyways. Okay, so you notice there's 3 of them, right? So 3 orbitals give you 3 out. Each of these 3 hybridized orbitals are called sp2 hybridized orbitals. Okay, sp2. And they're all equal energy, but they have different orientations. And so let me show you. Actually, I'll show you in a moment. I'll put these 3 together in a different slide because it's going to get too busy here. So now let me give you the third one. The third one is we're just going to mix, we're going to add in the third p orbital. So we got this one. So there's px plus py plus, and then coming into and out of the board, pz. And that's going to give you 4 new orbitals, right? Because you're putting in 4 of them. We've ran out of p orbitals, so there's no 4th p orbital. Now you're going to get something that looks like this, plus something that looks like this, plus something that looks like this, plus something that looks like this. Okay, and we're going to call these sp3 orbitals. Again, the number you put in is equal to the number you put out that you get out. And these would be called sp3 hybridized orbitals. Okay, so you get 4 out. So here's what happens in particular with carbon. If carbon needs to form a bond to one atom, what it will generally do is use an sp orbital, which is very directional, points in one direction. And then it'll put a lone pair into the other sp. Because see how there's 2 sps? So it'll do a bond with one and then put the lone pair in the other. If it needs to form a bond to, let's say, 3 atoms, it'll use sp2s. So actually, let me rephrase that. If it needs to form a bond to 2 atoms, it'll use the sp. So it'll do a bond to one atom with an sp and a bond to another atom with sp. If it needs to do bonds to 3 atoms, it'll use sp2s. And if it needs to do bonds to 4 atoms, it'll do sp3s. Okay, so the ability of carbon and other elements to mix these orbitals together to give us these hybridized orbitals gives them some flexibility in terms of how they form bonds to other atoms. Okay, so one of the skills, one of the problems that you're going to need to learn how to do here is to identify within a Lewis structure these schemes, these sp, sp2, sp3 hybridization schemes, okay? And it turns out it's really simple, okay? What you do is you say this. You look at the central atom and you count how many surrounding atoms it has. So let's suppose it has two. We're not going to worry about one surrounding atom because generally, if there's only one surrounding atom, there's usually no need for the atoms to hybridize. They'll just use regular atomic orbitals. So if you have two surrounding atoms, typically what you get, remember we said this was linear? I'm sorry, let's use AX. We're going to use the same scheme that we did yesterday. So AX2. So we said that was linear, and we said the angle was 180 degrees. Well, it turns out that's SP hybridization. I'll just write it, abbreviate it as hybridized. Okay, that ends up what happening. So if you have a central atom with two surrounding atoms, no lone pairs on the central atom, you get linear 180 and it's SP hybridized. And you can sort of see why that's the case. So here's your A. Remember the SP orbitals? Those two orbitals are pointing opposite directions. So then here's your X, right? It's going to form a bond to X. And it's going to form a bond. I'm not putting in the orbitals for the X atoms. I'm just ignoring that. I'm just saying X for the surrounding atom. Because, you know, if it's a fluorine or a chlorine or a bromine or hydrogen, it's going to have different orbitals. But we're talking about the orbitals for the central atom here. And that's an important aspect of the hybridization. Okay. So A, the central atom, has these two SPs. Right. So if it's AX2, it's going to use SP. Again, the essentially what happens is there are certain arrangements that are stable and lower in energy. So it's not like the atom has to think about it. Obviously it can't. The atom is just, you know, it's kind of like this, I guess. You know, if you imagine like, you know, someone's drawing these or building these holes in the ground, they're just certain energies that are stable and ones that are less, right? So like, you know, right here, this is stable. This is lower in energy. So is this one. So is this one. So is this one. So, you know, if I threw a ball in, you realize, hey, the ball is most likely not going to just land there and sit there because it has kinetic energy and potential energy. So when it hits the surface, it's going to bounce around. But you also realize that it might end up down here, right? And it might end up down here, and it might end up in any of those four different places. All of those are possibilities. So that's essentially what happens with these hybridized orbitals. Like if you mix an S with a P, you get an SP. If you mix an S with two Ps, you get sp2. And so there's certain arrangements that are likely to occur and other ones that are not. And so, you know, this is one of them, you know, where you have two surrounding atoms, and to get two surrounding atoms to maximize the strength of the bonds, you're going to use sp orbitals. And that's essentially what's going on there. It's kind of cool. Okay, so there's one possibility. The next possibility is what happens if, you know, it turns out it's stable when you have three surrounding atoms. So this happens with nitrogen and phosphorus, for example. It also happens with oxygen. The hydronium ion has three surrounding atoms. So this one we said, right, was trigonal planar. And this was 120. And this is sp2. So when you see a trigonal planar structure right there, you know it's sp2. I'm not going to write hybridized, so it is hybridized. And then what happens here? Here you get three of these sp2 orbitals. See the directions of these orbitals? 120, it's a trigonal planar, right? There's your 120. Okay. And then if you go back to the earlier part of the lecture when I was showing you these sp2 orbitals, you'll remember, oh yeah, one was pointing up, one was to the right, and one was to the left. And that's exactly, you know, that's exactly what we're showing here. There's three of them, right? There's three sp2 orbitals. And then you get up to AX4. This one's tetrahedral. and that's 109.5 degrees, and that's sp3. And then again, there's 4 of them. So what happens is you get these orbitals that look something like this. So there's your 4 X's. And those are 109.5 degrees. Okay. And then, you know, look, if you have lone pairs, so for example, let's say you have AX2, E2, that's like water, right? Then it's going to be bent. But remember, bent is 104.5 degrees. So really, it's the same hybridization as you see in the tetrahedral. And 104.5 is pretty close to 109. Really, what's happening is you have 2 of these orbitals. One of them has a lone pair. A second one has a lone pair. And then the other 2 have the X's. They're bonded to X's. Okay, so that's why the angles are a little bit different, but it's essentially sp3 hybridization. And if you have AX3E1, that's what we call trigonal pyramidal. And that was 107. That's also sp3. It's the same hybridization. It's just that what happens is only one of those orbitals has a lone pair, and then the other 3 are bonded to surrounding atoms. Okay, so that's what you're going to see in something like ammonia. So this you'll see in water. That'll be water, and this would be ammonia. Okay, for carbon, these are really the ones that we're concerned with, because this is essentially what carbon is able to do. It's got 3 different hybridization schemes. And you can go even further. Look, you can start saying, look, if we're in the 3rd or 4th row, we could start doing hybridization where we mix some of the d orbitals in there, and you get sp3d1 or sp3d2, and you know, you can keep going on there. But for the most part, these are the ones we're concerned with, because hybridization is really something that people use when they discuss organic chemistry, which is the carbon atom. Okay, so there's all the background on it. This chart right here is very helpful. I find it to be very helpful. In fact, you can extend the chart into here if you want to, and that allows you to do even more problems. But what I want to do is I want to look at a couple of example problems now. So let me bring up the Alex problems. There's just 2 that you need to do for this section. So the first one is tag all the sp2 hybridized carbon atoms in the molecule. If there are none, then check the box below. Okay. So sp2, so how do we figure that out? Well, there's a bunch of carbon atoms here, so you kind of got to go through each carbon and figure out what its hybridization scheme is. And here's how you do it. It's actually very, very simple. What you do is you look at the carbon and you count up the number of surrounding atoms that it has. And then you just use the AX2 is linear, so that's sp. AX3 is trigonal planar, so that's sp2. And AX4 is tetrahedral, which is sp3. So you want to actually, I would recommend remembering this, is that linear is sp, trigonal planar is sp2, and tetrahedral is sp3. Furthermore, remind yourself AX2 is the one that gives you linear, AX3 is the one that gives you trigonal planar, and AX4 is the one that gives you tetrahedral. And that will get you through carbon atom. Again, carbon is the one that we mostly use for hybridization. And we'll look at another type of problem where it's not carbon, but that's actually where it's mainly used. And so it's actually pretty simple if you think about it. There's just 3. AX2, linear, sp. Number of sp orbitals is 2. AX3, trigonal planar, sp2. AX4, tetrahedral, sp3. So sp, sp2, sp3. So if we want sp2, what you're going to have to get is AX3. You're going to have a central atom, carbon, with 3 surrounding atoms. And if you take a look, this carbon right here, the first one, it's got 4 surrounding atoms, right? 3 hydrogens and 1 carbon. So that's sp3. So that's a tetrahedral. So you get the shape, but you also get the hybridization. So there's 4 sp3 orbitals. Now you look at the second one. The second carbon is surrounded by 2 atoms. So it's AX2. It doesn't matter that that's a triple bond. I mean, it matters because the number of bonds, we're going to look at that in a moment. Actually, I'm going to go over it with this one. But in terms of determining the hybridization, all you need to do is figure out the number of surrounding atoms. If you have lone pairs, count them like a surrounding atom. It's electron groups, really. It's not surrounding atoms. It's really electron groups. So if you had AX2E2, that would be tetrahedral. Okay, so this one is AX2, so that's linear, that's sp. And then this third carbon atom, it's got 2 surrounding atoms, so that's AX2, that's linear, that's sp. So there aren't any sp2 orbitals in here. Now, one of the things that we want to be able to do is count sigma and pi bonds. And so I want to show you how to do that quickly. If you have a sigma bond, if you have a single bond between the central atom and a surrounding atom, it's got to be a sigma. Because if it only has one bond, those orbitals are going to point directly at each other. So that's called a sigma bond. Okay. So whenever you have carbon bonded to hydrogen, you can only have a single bond because hydrogen, the duet rule, can only have 2 electrons. So these are all going to be sigma. So this would be a sigma, this would be a sigma, this would be. Same thing here. As long as there's only one bond between 2 atoms, it's a sigma bond. But when you get multiple bonds, what can happen is geometrically, you get your sigma bond, right? Direct overlap. They're pointing toward each other. But now that region of space is taken up. It's eliminated from availability. So now any other bonds have to take over other regions of space. So what will happen is, you get a sigma bond. So, the atoms are here and the orbitals are here. But then you can have overlap between the p orbitals that are coming this way and overlap between the p orbitals that are going that way. So when you have multiple bonds, the second bond is a pi bond and the third bond is a pi bond. And that's why we generally don't see more than 3 bonds between 2 atoms, is because the sigma takes up the space in between the atoms, and then the pi takes up this space in this direction, and the other pi takes up this space in this direction. So you run out of space. It ends up being completely filled. There's no room for any more atomic orbitals. So you're stuck with 3 bonds, okay? So first bond between 2 atoms is sigma, second bond is a pi, and then the third bond would be a pi. So if someone asked you how many pi bonds are in here, you would say 2, because single bonds are always sigma. And then if you have multiple bonds, the first one's a sigma and the subsequent ones are pi. Okay, let's take a look at another example. Okay. So read the instructions carefully. Tag all the carbon atoms with pi bonds in the molecule. If there are none, please check the box below. Okay. So this is a different question. It's not asking us for hybridization, but let's do the hybridization of both carbon atoms. Hybridization is done for the central atoms, not for the surrounding atoms. Surrounding atoms don't need to hybridize. So we wouldn't generally ask what's the hybridization of oxygen here, but we would ask what's the hybridization of the carbon because it's a central atom. So let's start with this carbon over here. This carbon right here is surrounded by 4 atoms. So that's AX4. So that would be tetrahedral 109.5, but it would also be sp3. The second carbon over here, this one is bonded to 3 surrounding atoms, a hydrogen, an oxygen, and a carbon. So that's AX3, which is trigonal planar. So it's a flat part of the molecule. And that one would be sp2. Remember, trigonal planar is sp2. So sp, sp2, sp3. But now the question is, what about sigma and pi? Again, a single bond is sigma. So that's a sigma, and that's a sigma. Okay. That's a sigma there because it's a single bond. All the single bonds are sigmas. But now we have a double bond. So the first one is a sigma and the second one is a pi. Okay, it doesn't matter which one you call sigma, which one you call pi, it's arbitrary, but one of these is a sigma and the other one is a pi. Okay, so that carbon right there, we would tag that as having a pi bond. It actually has a pi bond to the oxygen atom, right? So the oxygen atom also has a pi bond. But there you go. Okay, let's look at another one. Tag all the carbon atoms with pi bonds. It's very simple. All you got to start doing is looking for the double and triple bonds, right? So any bond that's sigma, any bond that's single is going to be sigma. Any bond that's double or triple is going to have sigma and pi. So both of these carbon atoms, okay, both of them have pi bond, right? Because they both have a double bond. So this carbon has a pi bond, this carbon has a pi bond, okay? Okay, it's too late, but for this one, let's go through hybridization. So the first carbon here on the left here is AX4, it's bonded to 4 atoms, so that's tetrahedral, so that's sp3. Second carbon atom is bonded to 3 atoms, so that's trigonal planar, and that's sp2, so that's sp2. There is no sp in hybridization in this molecule. Now the oxygen atom here can also be hybridized because it is a central atom. So just to go over that real quick, this one right here is bonded to 2 atoms, 2 surrounding atoms, and 2 lone pairs. So it's really 4 electron groups. So that would be sp3. So this oxygen would be sp3 hybridized. Okay. The arrangement is bent, but that's the hybridization. Okay. Tag all the pi bonds in here. Okay, well, we've got 3 carbons. I'm going to go through all of them. The first one, sp3, right? Because it's got 4 surrounding atoms. So that's sp3. All sigma bonds, right? They're all singles, so they're all sigma bonds. Second carbon right here, all single bonds, sp3. Again, it's got 4 surrounding atoms. But now this third carbon is very interesting. This one is only got 2 surrounding atoms, so that's AX2, so that would be linear, and that would be sp. So that one right there is sp. And then finally, how many pi bonds? Looks like there's 2 pi bonds here. There's a pi bond, 2 pi bonds between this carbon and nitrogen, right? The first bond is sigma, the second and third are going to be pi. And there you go. Okay. Oops, sorry. Let me come over here. Okay, so the second type of problem is identifying hybridization schemes. Okay, so this one right here, they're small molecules, but they're going to have you go through substances that are not organic. These are inorganic compounds. This is an ion, actually. So this is the iodine tetrachloride ion, or tetrachloroiodide ion. Okay. This one, we want to find out what the hybridization of the central atom is. So here's what you do. You just look at the Lewis structure first. So let's, sorry. Let's come over here. Okay, so there's your ion, ICl4 minus. Okay, so again, this one's a little tricky because it's one of those expanded octets. You've got 4 surrounding atoms. If you go through all the Lewis structure, I'm just doing this because I've done it so many times. It would presumably take you longer to do the Lewis structure. But what you end up with is you end up with kind of extra electrons here. So I think you have 2 lone pairs here. And then the whole thing is negative. But let me check that because I'm not positive about this. You've got 7 for the iodine because it's in group 7A. And then you've got 7 for each chlorine because each of them is in group 7A. And then you got 1 extra because of that negative charge. So 28 plus 8 is 36. So if you have 8 to each of the chlorine atoms, right? 3 lone pairs in a single bond, that's 32. And then 34, 36. So there's 2 lone pairs on the central atom. So here's how you do this. You just count up it's the same charts we were talking about yesterday. Sorry. Okay, remember how we said that that was linear? And this was trigonal planar. and this was tetrahedral, and this was trigonal bipyramid, and this was octahedral. I'm not going to put the angles down, but there's obviously, but now I'm going to put the hybridization. SP, SP2, SP3, SP4. No, there's no such thing as SP4, sorry. SP3D1 is called, and then SP3D2. Okay, so the notation is how, it's the orbitals that you're mixing plus how many of them. So if you mix one S with one P, you have SP, 2 orbitals. If you have a total of 6 orbitals, you're going to have something like SP3D2. Now, why is there no SP4? Because there's only 3 p orbitals that you can mix, so you can't have 4 p orbitals. So SP3D2 has an S plus 3 p's plus 2 d's. That's a total of 6 orbitals. So that's going to be your hybridization scheme. But notice this one doesn't have 6 surrounding atoms. It only has 4. So why isn't it tetrahedral? Because of those lone pairs. The lone pairs are also part of the hybridization. So if you have AX4E2, then that is also going to be SP3D2 because you have a total of 6 electron groups. Okay, so it's going to be SP3D2. So if you had something like, let's say you had AX4E1, well, now you've got a total of 5 groups, so it'd be SP3D1. Okay, so all you got to do is count up the surrounding atoms and the lone pairs, and then pick from this chart SP all the way through SP3D2. I've never heard of any others than these ones that are in this list. So let's come over here and look at one more. And again, I guess we'll draw the Lewis structure here. They're giving you these like expanded octet ones in here. They're not doing the simple ones, they're doing the more complicated ones. So this is XEF2. Remember, hybridization is a phenomenon of the central atom. Okay, the idea is the central atom uses hybridized orbitals to form bonds, to form stronger bonds. The surrounding atoms do not need to form bonds to separate atoms, only to one, only to the central. So they are going to use their traditional atomic orbitals, S or P or D. Okay, so XCF2, well, again, this is one of those kind of exotic molecules. XCF2. So all you just got to do is get this Lewis structure right. So XCF2, it's not XCF2 minus or anything like that. It's not an ion. Okay. This has 8 electrons. Each of these has 7, right? Group 8A, so it has 8. Group 7A, so it has 7. So is that 14, 22? We've already used 4. So we're down to 18, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. So we should still have a total of 22 electrons. Looks like we do. So now, again, here's what you do. You say, look, A, X2, X1, X2, 2 surrounding atoms. How many lone pairs? 3. Okay, so AX2. So how many electron groups? 2 plus 3, 5 electron groups. Okay, so then you go, okay, well, which one's the one with 5 electron groups? Well, here's 2 electron groups. Here's 3 electron groups. Here's 4 electron groups. 5 electron groups. 6 electron groups. So there you go, 5 electron groups. So sp3d1. Okay, it's a small molecule, only 3 atoms. Okay. And none of these are organic. They're not giving you any with carbon in there. Let's try this one. Identifying hybridization in a small molecule. What is the hybridization of the central atom in the beryllium fluoride molecule, which is BeF2? So, you know, XDF2 was sp3d1. So would this one be sp3d1? And the answer is no, because we have fewer electrons around the central atom. Okay. This is beryllium, which is only a group 2 element. It's actually on the second period. So that's the issue there. So let's take a look at this one, BeF2. Okay, so beryllium difluoride. Okay, well, let's draw the Lewis structure. Okay, let's count up the number of valence electrons. Beryllium is in group 2A, so it has 2 valence electrons. Fluorine is in group 7A, so it has 7. So that's 16 electrons. I've already used 4, so we're down to 12. 2, 4, 6, 8, 10, 12. And there you go. So there's your Lewis structure. Now you might make an argument, hey, wait a minute, what about the octet rule? Beryllium is, you know, if you want to make this octet, you can. What you would do is you would just convert these to double bonds. People argue over whether this is what happens or not. So is it a single bond or is it a double bond? The problem with the second structure is you have a formal charge of +1 for fluorine, whereas in the first one you have a formal charge of 0 for fluorine. And you know, the formal charge argument would be in favor of the first structure, but the octet rule would be in favor of the second one. So people argue over which one's correct. Doesn't matter, actually, it turns out, because the central atom doesn't have any lone pairs in either structure. So in both cases, it's just AX2, right? So again, that's going to be linear, and that's going to be sp. So in that case, the beryllium is the hybridized orbital, and it is going to have sp hybridization. Okay, so again, the idea would be beryllium has these sp orbitals, they're opposite directions, bonded to the fluorine atom. I'm not putting in the orbital for the fluorine atom for either of them. And then you're going to have a linear arrangement, 180 degrees. Okay, so there you go. So that's it for hybridization. There's really just 2 types of problems there. Now, the last topic is molecular orbital theory. So let me go through that one. Okay, so 9.6 is molecular orbital theory. I'll just put molecular orbitals, if that's okay. And I'm going to abbreviate them MOs. Okay, often chemists will refer to them as MOs. Molecular orbitals are essentially what happens when we're just going to look at what are called homo, which means one, or which means the same, nuclear, same nucleus, meaning the same element, hydrogen, hydrogen, oxygen, oxygen, nitrogen, nitrogen, diatomic, 2 atoms, molecules. And the name molecular orbital is for molecules. So molecules, right? Although we can extend it to ions. Okay. Now here's the idea behind MOs. MOs are probably more accurate in describing the behavior of molecules and their structure, but they are very difficult to calculate and they require enormous amounts of computing time. So even with the advanced supercomputers we have now, it's still a lot of work to do molecular orbital calculations, but they're pretty good at predicting properties of molecules, at least in some cases. So the idea is essentially this. I'm going to use hydrogen as the simplest case. You know, in hydrogen, the only orbital really that has electrons is the 1s orbital, right? So I'm going to call this H1s, comma A. A meaning atom A. And then I'm going to bring up another hydrogen atom. And there's its 1s orbital. And I'll call this atom B. Okay, so H1s, meaning that's the 1s orbital for the hydrogen. So H1s. And then it's atom A, and this is atom B. So atom A, atom B. So that's the notation I'm using here. And what I'm going to claim here is that what happens is kind of like hybridization, except that the difference here is the orbitals that are mixing are from different atoms. So remember in hybridization, you'd had sp2, sp3, sp. Those were the orbitals of one atom, the central atom. They were mixing. That's an internal thing. Now we're saying no. What's going to happen is these orbitals are going to overlap and they're going to mix together from different atoms and form a new orbital that's called a molecular orbital that gives it a stronger bond than if they were separate. Okay, so this is called a molecular orbital. These two orbitals will mix, but again, think how you're getting two of them, right? You have two orbitals, so you're going to get two orbitals out. And here's what's interesting about this. What you get is, here's the nucleus of the first atom and the nucleus of the second atom. You get a large amount of electron density between the nuclei. Okay, so that's the first one that forms. And we're going to call this sigma 1s. So there's that notation of sigma again, right? So this is a sigma bond. And that molecular orbital has a lot of electron density between the nuclei. So I'm trying to draw it that way. People draw them different ways, but that's one way to draw it. Okay. This one is lower in energy than the atomic orbitals. So the argument here is that the hydrogen molecule will form, right? Because when those two orbitals overlap with each other, they merge, the orbitals merge into a new orbital that improves the amount of electron density between the two nuclei, and that's going to hold the molecule together, sort of like a glue. Okay, so that's a sigma bond. But you get a second bond too, and it turns out this one's higher in energy. So there's your nuclei, and it looks like this. And right here is what's called a node. It's called a node, or more technically, a nodal plane, because it's two-dimensional. And there's no density, there's no electron density. So in fact, most of the electron density is away from the nuclei. It actually is higher in energy. So this is higher in energy than the atomic orbitals. So here's our energy level diagram. This one's above, higher in energy, and this one's lower in energy. So just like, you know, balls falling, or the Aufbau principle, things fall down, right? So lower in energy, same thing here. So what we'll claim then is that when this molecule forms, something interesting happens. This atom has one electron spin up. This atom has one electron spin up. Those two electrons go into this orbital here. Spin up. One of them has to change its spin because of the Pauli exclusion principle. So these two electrons here are these right here. And then this one, it doesn't have any electrons in it. It's empty. And this one we're going to call sigma 1s. And just to say that it's higher in energy, we're going to call it star. So this is sigma 1s star. Higher in energy. This one is sigma 1s. Lower in energy. So the one that's lower in energy is 1s. The one that's higher in energy is 1s star. If you wanted to, once this molecule forms, so this is now H2, right? So we had HA plus HB. Now we're going to have a molecule HA with a bond to HB. And this is going to be a sigma bond. Okay. And the molecular orbital is called sigma 1s. And it has that particular shape there. Okay. It gets more complicated when you get into the second and third row, because now you have more types of orbitals you can mix together. You can mix S's together, P's together, and you can get sigma and pi bonds and all this sort of thing. So what I want to do, though, is I want to switch you to seeing So let me create a new window here. And I'm going to have to search it. Oops, sorry. I'm going to have to search it. I'm going to fast forward now to what are called the molecular orbital diagram for diatomics. And you can look these things up. There's two of them that we need. One is for a few of the elements, and the second one is for a few of the other elements. But I want to show this to you. Okay. You just have to be careful because yeah, that's not a good one. Sorry. Okay. Oh, I see. Okay. Okay. So here's how it works out. This is one of the possibilities. Is if you take a look at how the p orbitals mix. Again, diatomic, so we're talking about two atoms. So on the left side, what are shown are three atomic orbitals from an atom. So it could be a carbon atom, for example. 2py, 2px, 2pz, okay? So those are your three atomic orbitals. And then on the right is 2py, 2px, 2pz. So that's the second atom. Those atomic orbitals will mix with each other to give these new molecular orbitals at the center, okay? And notice the notation, pi sub y, sigma sub x, pi sub y star, pi z, pi sub z star, and sigma sub x star. Where it has a star, that is called an anti-bonding orbital, and it is generally higher in energy than the ones without the star. So you have bonding orbitals that don't have a star, anti-bonding orbitals that have stars. It's just the way that they mix together, okay? Now the problem here is that people have calculated molecular orbitals for many different substances. So really what you want to do is you want to find the energy level diagrams. You're not going to actually create these yourself. You have to find the right ones for each element. So some of the elements have one diagram, some of the other ones have different diagrams. Okay, I apologize, it's taking me so long to get this. So what I'm going to do is I'm going to type in molecular orbital diagram for, let's do nitrogen. Okay, so here's for N2, dinitrogen. Okay, here, hold on a second. Make this a little bit bigger. Okay, so here is the molecular orbital diagram for nitrogen, N2. So here's what you do. You first draw out the electron configuration for the element. So nitrogen is 1s2, 2s2, 2p3. So see how there's the 2s and there's the 2p? 2p is higher in energy than 2s. So there's your 5 valence electrons for nitrogen. Then you do the same thing for the other one on the right side. So this is the other nitrogen. S, 2s2, 2p3. Notice they're not showing the 1s2. You can put that in there. It's going to be lower in energy, but we're not going to need it. So then what you do is here's the diagram that you look up. You look up this diagram. It's in Alex. It'll give it to you. You have this diagram, and what you do is you use the Aufbau principle. So you fill from the lowest energy molecular orbital to the highest, all the way till you run out of electrons. So if you count up the number of electrons you have 5 from this nitrogen, 5 from the other nitrogen, so that's 10. And you put them into these orbitals here till you run out. Now notice what happens. You have sigma 2s has 2 electrons. Sigma 2s star has 2 electrons. So you have electrons in an anti-bonding orbital and electrons in a bonding orbital. Then you have electrons in these orbitals here and none in here. And so what you can do is you can actually look at a couple of different properties of the molecule to determine how strong the bonding is. And that's called bond order. So I'll show you how to do that calculation. And you can also look at the magnetic properties of the molecule. If there are unpaired electrons, then the molecule will act like a little magnet. It'll be paramagnetic. If it doesn't have any unpaired electrons, then it's diamagnetic and it repels a magnetic field, okay? So if you look at this molecule, I'm gonna go through a couple of examples with you. Okay, so let's take a look at this one. So drawing the MO energy level diagram for a period 2 homodiatom. Okay, I've never heard that term, homodiatom. Generally they're called homodiatomics, okay? But here's a diatom, a homodiatom, that's fine. So 2 atoms, the same element, homo means the same element, atoms, 2 atoms. We're not gonna do any more complicated than that. Do notice that they put an ion in there. So they do have 2 extra valence electrons because it's B2 -2. Draw the molecular orbital electron diagram for the B2 -2 molecular ion. Be sure your diagram contains all of the electrons in the ion, including any core electrons. So now they want you to do the core electrons, okay? There is debate among chemists as to whether it's necessary to do that. The movement over time is towards more complexity. So here they want you to do the core electrons. So what you got to do is you got to look up the diagram. The diagram is in your textbook. So if you go to the ebook in chapter 9, section 6, it's going to show you the diagram. But you got to pick the right one. There's 2. There's one for beryllium, lithium, beryllium, boron, and carbon. And then there's another one for nitrogen, oxygen, fluorine, and neon. So just make sure you use the right one. So this is the one you want to use, the one for boron, okay? So let me show you how to do this one. Okay. So it's B2 -2, okay? So you want to use the right one. So the one that you're using is it's the same one for groups 1A through 5A. Okay, so that's really going to be lithium through nitrogen. And then there's a separate one for groups 6A, 7A, and 8A. And so that's oxygen through neon. Okay, so for this one, because it's boron, we're going to use that one. Okay, so let me show you. Actually, let me do this. Oh. Okay, sorry. There we go. Excellent. Okay, this is what I wanted to show you. So let me stop share here. Come up here and share this one. Okay, so this is the one for groups 1A through 5A. So that's the molecular orbital diagram for any element groups 1A to 5A in the second row. Okay, so notice it starts at 1s. So we're going to actually do the core electrons here. And then it has the 2s and the 2p. And what you're going to do is you're going to take the number of valence electrons. So you can take the electron configuration for each element. But then remember, it's -2, so you're going to add in those extra electrons. And then you're going to use the Aufbau principle to fill up these molecular orbitals, right? So the left side is atomic orbitals for the first atom. The right side is the atomic orbitals for the second atom. They're going to mix together to give you these molecular orbitals, okay? So let's take a look at how to go about doing this one. Okay, so it's B2, so B2 -2. Okay, so let's first find out the number of valence electrons. Boron is in group 3A, so 2 times 3. And then you've also got an extra 2 electrons. So there's 8 valence electrons, okay? So now I'm going to draw the this is 1s, 2s. This is the electron configuration for the boron atom. Okay, so what's boron? Boron is an element. So boron is 1s2, 2s, 2p1, right? Oh, I'm sorry. I have those are the number of valence electrons. So I'm wrong about this because we don't want to do valence electrons because they gave us the core as well. They said explicitly in the instructions, do the core. Okay, so how do you do that? If you're going to include the core, boron is element number 5. So 2 times 5 is 10, and then it's -2. Okay, so it's a total of 12. Okay, now, so this is the first boron. And then you have the second boron as well, right? So what about the second boron? I'm going to put that all the way over here. 1s, 2s, 2p. Okay. Now I'm going to draw in the molecular orbitals. So this is the first boron. This is the second boron. If you want to use the notation like I did with hydrogen A and B. Okay. Now you're going to do the molecular orbitals, and they're going to be in the center. So the Alex table doesn't do this, but I'm going to do it this way. I'm going to draw little lines just to show you what's going on. So when those 2 atomic orbitals, the one on the left and the one on the right, mix, you get 2 new molecular orbitals. One's lower in energy and the other one's higher in energy. And this one is called sigma 1s, and this one's called sigma 1s star. Okay. Now, boron has a total of 5 electrons, a total of 5 electrons. We've been talking about valence electrons for a couple chapters now, but it has a total of 5 electrons, 3 valence electrons, right? So I'm going to put in the 5 electrons, including the core electrons. That's for boron, but it's -2. So what do? You put in 1 electron on each of, and in fact, let me do this. Why is that not erasing? You put in the extra electrons here. Okay, so just assume symmetry, that 1 extra electron on each one because of the -2 charge. So now you have a total of 12 electrons. Okay, there's 8 valence electrons, but we need the total number. Okay, so now what happens when you start mixing the 2s? Something very similar. You get one that's lower in energy than the atomic orbitals, and you get one that's higher in energy than the atomic orbitals. So this one's sigma 2s, right? See the notation? It's just sigma, it's a sigma bond. And if it doesn't have the star, it's called a bonding orbital. If it does have the star, it's called an anti-bonding orbital, okay? The anti-bonding orbitals are higher in energy than the atomic orbitals. So if an electron goes into an anti-bonding orbital, that makes the molecule less stable. Okay, I'm going to say that again. The anti-bonding orbitals are higher in energy than the atomic orbitals. Remember, the atomic orbitals are over here. The anti-bonding is higher in energy than the atomic orbitals. So if electrons go into the anti-bonding orbitals, that makes the molecule less stable. It weakens the chemical bonds. If electrons go into the bonding orbitals, those are lower in energy than the atomic orbitals, that stabilizes the molecule and makes the bonding stronger, okay? So anti-bonding orbitals weaken the molecule, bonding orbitals strengthen the molecule, okay? So now what about the P's? Well, the P's mix together, but there's a lot more of them. There's 6 of them total, not just 2. So you're going to get more complicated mixing. So here's what happens. You get 2 orbitals down here that are lower in energy than the atomic orbitals. And then you get even another one that's even still lower, but it's a little bit higher than the P's. So you get 3. I'm not drawing them very big here. Let me make that bigger. So you get 3 there. Think about it. If you're counting orbitals, we're mixing 6, so we got to get 6 out. So then you get 2 that are higher in energy than the atomic orbitals. So those are antibonding orbitals. And then you get one that's even higher. Okay. Now, what's the notation? These are called pi 2p. This is called sigma 2p. This is called pi star 2p. And this is called sigma star 2p. Okay, you'll see that drawn better on the diagram. Just make sure you use the right diagram. So groups 1A through 5A, you use this diagram. Groups 6A, 7A to 8A, it's a slight variation, just looks a little bit different. Okay, just switches the orders of the sigma and pi stars. Okay, so now here we do the Aufbau principle. So how many electrons do we have in here? We have 12. So you just take those 12 and just start piling them in from low energy to high using the Aufbau principle till you run out of electrons. We have 12. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 9, 10. Okay, remember Hund's rule? If these orbitals are in the same energy level, you do spin up, and then spin down, spin down. So 9, 10, 11, 9, 10, 2, 4, 6, 8, 10. Well, we're done, right? 2, 4, 6, 8, 10, 12. So we're done. So here's what I'm going to do. I'm going to write the notation for this diagram. Okay, this is the diagram over here. Okay, now let's do the notation. What you do is you write the name of the orbital, sigma 1s, and then how many electrons are in it. The next one up I'm sorry. I was confusing myself. The star goes down here, 1s star, and then you put the 2 above it as a superscript. Sigma 1s2, sigma 1s star 2. Next one is sigma 2s. There's 2 in there. So it's kind of like electronic configurations like we did with the atoms. Okay, so I've done all 4 of those. Then we have this one, pi 2p4. Okay, sometimes people put them in parentheses. Okay, like that, just so you can sort of see them a little bit better. Now, I want you to do, I want to show you what's called bond order calculation. Okay, here's how you calculate bond order. What you do is you count the number of bonding electrons and you subtract from that the number of anti-bonding electrons. And then you divide it by 2. You divide it by 2 because a bond in general is considered 2 electrons. So dividing by 2 takes the electrons and turns it to the number of bonds. So this is an interesting idea. The idea here is essentially you're saying, look, anti-bonding electrons destabilize the molecule. Bonding electrons stabilize it. So take the difference. If you have more bonding electrons, you're going to have bonds. You're going to have net bonds. Divide it by 2 so you get the number. And what you're going to end up here is this actually works out pretty interestingly. So let's count up the bonding electrons. 2, 4, 8. And then we're going to subtract from that the anti-bonding electrons, which is 2, 4, right? Just the electrons that have the stars. And then you divide that by 2. So that's 4 over 2, so that's 2. So the bond order is 2. So in other words, this molecule appears to be sort of like a double bond, right? Essentially, it's equivalent to a double bond. Okay, so it's very powerful. I mean, there's all kinds of things we could talk about in terms of this, but it's a very powerful technique for figuring out the property of the molecule. It turns out that this B2 negative 2 ion, it probably behaves a lot like a double bond, and you wouldn't be able to get that very easily out of a Lewis structure. You wouldn't be able to get it out of hybridization. Molecular orbital theory is essentially required to be able to look at this molecule. Okay. So you can also look at its magnetic properties. There are no unpaired electrons. Everything is paired up, spin down. So it's diamagnetic. So we would also claim this molecule is diamagnetic. Okay, no unpaired electrons. If it had unpaired electrons, we would call it paramagnetic. Okay. All right, let me see if there's another one. Okay, I'm going to show you one now. Let me just download this picture. There we go. I didn't actually have to download it. I just needed to open it. Oops. So draw the MO energy diagram for period 2 homodiatom. Same problem. We're going to do it for the O2 molecule now. Okay, include the core electrons. Okay, so the diagrams are in Alex. You can just download them, open them up into a different window. You don't have to download them. You can just open up into a different window. They're also in your textbook. But you want to make sure you use the right one. It's the same for groups 1 through 5, and it's a different one for 6 through 8. So oxygen is in group 6A. So you want to use the right one, right? So let me share the right picture here, just so that you see it. Okay. Oops, sorry, that's the wrong one. Here we go. So there's the right one. So this is the one that you would use for oxygen. Okay. So this is from Alex, and really it's a very minor detail, but it makes a big difference. So what happens here is if you look at the top, the sigma and the pi up at the top are flipped in oxygen, groups 6A, 7A, and 8A. So you get a slightly different diagram. And what that does is it ends up changing the arrangement of the electrons. Now this switching, this different diagram is a result of some phenomena that we're not going to talk about in this course. But this is the diagram we would use for O2 or N2, I'm sorry, O2 or F2 or F2 minus or F2 plus. If it's positively charged, you remove electrons. If it's negative, you add electrons. Okay. You could also use it for Ne2, neon, dineon. Okay, but there's your diagram right there. So let me work on this one here. So we're going to do O2. Okay. And what I'm going to do is I'm going to try to draw this maybe a little better than I did before with the B2 2 minus. Okay, so remember that's the first oxygen atom on the left. So there's one of the oxygen atoms. So we're essentially saying, look, it looks like this, 2 atoms, right? And then all the way over here is the second atom. And it looks just like the first one. The energy level diagram is the same. But we are including the core electrons. Okay, then they're going to mix to give you new orbitals. So again, I like to draw these little lines just so I can sort of see a little bit better what's happening. Those 2 orbitals on the left and right are mixing together to give you 2 in the middle. And the notation is the same as with the other one. Okay, same thing here. Now it gets a little bit crowded when you get up to these P because there's so many of them, right? There's 6 of them. So how do you put all 6 in there together? So it looks something like this. You get one that's way down here, which is sigma 2p, okay? Then you get 2 that are a little bit higher, which is pi 2p. And then you get 2 that are higher than the atomic orbitals. So that's pi 2p star. So right, the ones that are their anti-bonding orbitals are higher in energy than the atomic orbitals. And then you get one more, which is sigma 2p star. So notice here, all the stars are up at the top, right? And all the ones that are not stars are at the bottom. So then you count up your electrons. Now this is not O2 negative or O2 positive. It's just O2. But be careful, not valence electrons, because in this Alex problem, they want you to include the core electrons. So go to the element number. The element number for oxygen is 8. So 2 times 8 is 16. And then you just do the electron. Okay, let's do the electron configuration for oxygen. 1s2, 2s2, 2p4, right? There's your 8. So for each of them, it's 1s2, 2s2, 2p4. So what that does is it allows you to get this 1s2, 2s2, 2p4. 1, 2, 3, 4. If it was -2, you'd put an extra electron on each oxygen. If it was +2, you'd take away an electron from each oxygen. If it was +1, you just take a 1 off of one of the atoms. Okay. So then you do 1s2, 2s2, 2p4. So that's all chapter 6 so far. Okay. Now we do the molecular orbital theory. Off-bow principle, right? Electrons, these electrons on the left and right start piling in to these molecular orbitals. Okay, I can already see that you've got 8 right there, so I filled them in. And then you've got another 4 over here on the left and 4 on the right. So 1, 2, 3, 4, 5, 6, 7, 8. See how I did that top part? I included Hund's rule. Those orbitals at the top there that I filled in, those ones have more than one orbital of the same energy. So you got to do spin up, spin up. And then if you got more, then you could do spin down, spin down. Okay. So it's kind of cool. So all these orbitals. So let's go through and let's do our bond order. So how do you do bond order? The number of bonding electrons minus the number of antibonding electrons divided by 2. So bonding would be here. Let's do the bonding in blue. So those would be bonding. So the bonding ones are the ones without the star. That's simple. Okay, so if you add all those up, you got 2, 4, 6, 8, 10. Okay, now let's do the antibonding. The antibonding, I'll do those in red. So there's 2 there. There's 2 there. So that's 4. And then you got only 2 there, right? Because we ran out of electrons. We had to stop at 16. 2, 4, 6, 8, 10, 12. Ooh, 14, 16. Yeah. So now how many do we have in red? It looks like it's 2, 4, 5, 6. Okay. Divide that by 2 to get the number of bonds. So that's 4 over 2, so that's 2. So it's a double bond. Now, it turns out that's interesting because it's actually consistent with the Lewis structure. The Lewis structure predicts it's a double bond, right? So molecular orbital theory confirms that, right? That's what a theory should confirm any earlier theory. Now, so now the next issue is, what about paramagnetism? Okay, so remember, if you have unpaired electrons, you're going to have a paramagnetic molecule. So there's 2 up there. So actually there's 2 unpaired electrons. So it's 2 unpaired. So that's paramagnetic. If you don't have any unpaired electrons, it's diamagnetic and it repels a magnetic field. So you've got a magnetic molecule. It's kind of cool. O2 is actually magnetic. We don't observe it as a gas because gas molecules have so much kinetic energy. But if you cool it down to a low enough temperature and liquefy oxygen, it actually becomes a magnetic property, and you can actually test that. You pour it as a liquid and you can see that it's actually a magnetic field. Produces a magnetic field. It's kind of cool. Okay. So there you go. So that is the molecular orbital theory. Okay, predicting bond order, cool, diamagnetic, magnetic, cool. Let me show you. I'm not going to go through the whole thing because this has been a long lecture. But I want to show you one more problem. And I'm just going to do part of it. And this one gets at both of those issues. So is it stable? Is it diamagnetic or paramagnetic? And what's the bond order? So I'm just going to do the first one. which is Li2 plus. And stable meaning, is there a bond order that is greater than 0? Okay, so if you end up with a bond order of, 0, it's not stable. Okay, if you end up with a bond order of 1, it's stable. That's kind of a primitive way of looking at it, but that's what we'll do. Okay, so let's do Li2 plus. So Li2 plus, let me stop sharing here. Okay, now again, we're doing this on Alex, we'll probably want to have the entire diagram. Okay, so what I'm going to do is I'm going to write it out for lithium. So here's, well, let's do it this way. So here's 1s and there's 2s. And then there's 2p, but we're not actually going to need the 2p, just so you know, because we don't have enough electrons. Remember, lithium is element number 3. So if there's 2 lithiums, that's 6 electrons. So that's not the number of valence electrons. That's actually the number of total electrons from the element number. So that's 6, but then we're going to have a plus. So we subtract 1 to get 5. So we don't have very many electrons here. Okay, so there's your first lithium. I'm going to do the second one over here. So we're not going to have to worry about the P's. And then what happens? These mix to give you sigma 1s and then sigma 1s star. And then these mix to give you sigma 2s and then sigma 2s star. Now you don't actually have to worry about the P. We don't have enough electrons to get up there. So if this was like O2 plus or N2 plus, then we would have to worry about that. And remember that sort of flipping, the diagrams change a little bit when you get to oxygen to group 6A. That's not an issue till you get up there, right? We just don't have enough electrons to deal with that problem, okay? So here's what I'm going to do. You got 5. So what you do really is just do the, the configuration for each atom. 1s2, 2s1, right? Lithium is 1s2, 2s1. But we have a plus, so we got to lose one of those 6 electrons. So it's up to you which one you want to take. Just make sure you take one out at the top, not at the bottom. So I took out the one over here on the right, but you could have taken the one out on the left. If it was +2, you would take out one from the right and then one from the left. So when they go out, when you take them away, you go from top down. Okay. So there's our 5 electrons, right? I said we had 5 and there we go. Okay, so now we do the Aufbau principle. We got 4 electrons here. So they go into here, 1, 2, 3, 4. And then we only got 1 here, so it goes into there. Oh, wow. So you've only got 5 electrons. So now let's do the configuration. Sigma 1s. And, usually actually they put it on the outside like that. Sigma 2s. Oops, that's wrong, right? It's sigma 1s, sigma 1s star. I'm going to put the exponents, the superscripts, on the outside. That way it's a little easier to see. Okay. And then you have sigma 2s. But it only has 1, right? There's just 1. That's half a bond, actually, if you think about it. So now let's do the bond order. Bonding electrons, so these are bonding here. This is bonding here, so that's 3. Minus the anti-bonding, that's here, that's 2 divided by 2. So you get a half a bond. So the molecule, is it stable? Well, it's somewhat stable. It's greater than 0 for bond order. So it has some level of bonding, so it should exist, okay? Then the issue of magnetism. These are paired, so those are diamagnetic. but you have one unpaired electron. So you have an unpaired electron. So that makes it paramagnetic. Okay, that's pretty simple. So the diagrams are the key. Make sure you have the diagrams available to you so that you can, fill these out. Off-bow principle from low to high. If it's an ion, remove electrons or add electrons, depending on whether it's positive or negative, and then you're set. Okay, so that pretty much is what we're doing. Counting sigma and pi, we went over that. Okay. Let me just real quickly though, I want to show you there's one more type of problem in here. And I'm not going to, there we go. I want to go over the pictures a little bit. So these are the molecular orbitals. Okay. So here's what they tell you. Let's take a look at this one. Study the following sketch of a molecular orbital in a homonuclear diatomic molecule. The MO was formed by combining 3s atomic orbitals from each atom. Okay. So this could be like sodium. Sodium is 3s1 is the valence shell, but it could be anything beyond that. So here's the idea. If you, the dots there in the center are the nuclei. If you see a little region in between the nuclei that's empty, see right there, that's called a nodal plane. We talked about that with hybridization. If you see the nodal plane, that means it's an antibonding orbital, okay? And if you don't see the nodal plane, then it's a bonding orbital. Okay, so there's your nodal plane. It's an antibonding orbital. That means it's higher in energy than the atomic orbitals, and it's an antibonding orbital. Now, what about writing the symbol for this? Well, you know it's from 3s. So it's either sigma or pi, and here's the deal. If you only have 2 lobes, it's a sigma. If you have 4 lobes, it's a pi for the antibonding. For the bonding, if you have 2 lobes, it's pi, and if you have 1 lobe, it's sigma. So actually, I'll just real quickly show you the picture here. So let's do sigma and pi. So sigma is going to look like this, and then pi is going to look like this. Remember we said there's 2 regions in the pi bonds? So it looks like that. So that's a pi. And then your sigma star is going to look like this. There's your nodal plane in the center. And then you got pi star. Pi star is cool. Pi star looks something like this. You get a nodal plane through here. Okay, so there's your pi star. That's essentially what they look like, from a cartoonish perspective. And then you got it. Okay, so like I said, if it's a sigma star, you can have a nodal plane. If it's a pi star, you're gonna have 4 lobes, and you're gonna have a nodal plane. And then if it's a sigma, you're gonna have just 1 kind of region, and if it's a pi, you're gonna have 2 regions. Okay, so there you go. So just to wrap this up, coming back to this one, write the symbol. Okay, so you've got, a low nodal plane, but it doesn't have 4 lobes, it only has 2. And then the name of the orbital that it's made out of is the 3s. So this would be a sigma 3s star. And it's an antibonding orbital because you see that nodal plane. And then it's higher in energy than the atomic orbitals. Antibonding orbitals are higher in energy. Bonding orbitals are lower in energy than the atomic orbitals that they're made of. Okay, let's look at another one. Ooh, wow, this is interesting. Okay, so take a look at this. This is very interesting. So you've got your 2 atoms there. This one's tricky. It's kind of tricky. It's made from 3p's, okay? So it's 3p. There is no nodal plane. The bonding region is, I mean, the electron region is primarily right in the middle in between the two nuclei. Okay, so that means it's a bonding orbital. The only question is it a sigma or is it a pi? Okay, so it looks like there's a lot of region up above and a lot of region below. So that's the way they're depicting this. So this looks like a pi. So this is a pi 3p. And there's no nodal plane, so it's not pi star. And so it'd be pi 3p. And then it's bonding because, you know, look at all the electron density between the nuclei, no nodal plane, so that's bonding. And then bonding orbitals are lower in energy than the atomic orbitals. And there you go. Okay, so play around with those. Those ones are kind of cool. And that pretty much wraps up that section. Those are the 4 problems. I guess I went through all 4 of them so that you can get through those. Looking at chapter 9, it looks like I've changed the date to the 4th. Okay, it was the 3rd, but I changed it to the 4th just to give you a little bit more time. So I hope that that helps you kind of get through all of it. And good luck. Let's see. Any other announcements? One announcement about Chem 12 for those of you that are taking Chem 12. If you haven't registered for Chem 12 because of you know the registrar saying you haven't finished this course, just make sure you email the Department of Physical Sciences. You can email viola.evans. I'll just put that up here. viola.evans@kbcc.cuny.edu. And what she'll do is she will give you a permission. I mean, you probably already know that because you took Chem 100 or something like that. But Kingsborough, they don't let you register for the next course in the sequence until you pass it. But that's kind of ridiculous. So most likely you're going to pass this class. So just email her and just say, look, you know, I'm taking 1100 with Lloyd and I'm definitely passing the class. I want to take 12 and I want to get into the section I want. And then you'll be set. She'll help. She'll give you the permission for that. For just find out what section you want to add. And you know, you will have an option in the fall. The chemistry is being run for Chem 12 in just like it's being run for 11 during the summer. You can pick, you know, the section that does hybrid, or you can pick the section that's completely online. The section is completely online. You pick the A lab, and the section is hybrid. You pick the B lab. Okay. And so have a great day, and I'll talk to you later.